Hey, good morning, dynamic students. It's almost time for the fun to begin here. I've got 9:28. I don't have my cell phone. Probably should go get it. But let's see who we've got on board here. We've got, oh, a good crowd. Stuart, Ryan, Nicholas, Braxton, Ashley. We've got a good crowd. You have 1 minute before class. Did you have any questions? Nobody has any questions for me. Do you have any questions? Well, I guess we could get started. Now, I just graded your homework, and most of you seem to know how to do homework number 18 okay. I think most everybody got a 4, but there were some that didn't. But number 19, we had a misunderstanding, I guess. I wanted you to do this example 1612. For homework, but I wanted you to have the angle be 30 degrees. I wanted an angle of 30 degrees. So maybe we should go over that. So about half of you got 2s because I guess you misunderstood. Maybe you thought it was supposed to be like the one in the book, which is 45 degrees. So I haven't figured out a way of making peace in the valley with you guys. If this was a normal semester, I'd just have you do it over again and we wouldn't count it. But I don't know how to do that when you send your stuff in on the computer. I'll try to treat you fair, though. If we have to, we'll certainly what's the word? Curve the homework. So the people with even though you got a few 2s here and there, you can still get a very high homework score when we curve it. But my concern is you guys understanding this stuff. See, I'm not as worried about grades as you are. I'm worried about you guys understanding this stuff. So let's go over this 30-degree business. And those of you that got 2s, you're probably so mad that you can't concentrate. But try. Try to concentrate. Okay, let's see here. Totally organized here. Yeah, you did that homework 18 just fine, most of you. Okay, now there's 3 ways to do this problem. One way is with the absolute method. And another way is with the CZ something. How's that go? CZV. It's Monday morning. Center of zero velocity. It's the ICZV method. And the third way is the relative motion method. Now, I've shown you these two methods here, but I'd like to show you the relative motion method for solving kinematics of rigid bodies. That's what we're talking about here. We're talking about kinematics of rigid bodies. And there are three methods. Now, in the absolute method, I went through that. And here's the equation. But I'm not going to go through it again. I'm just going to give you the equation. We developed this last time. You could watch the YouTube. It's on YouTube. But it goes like this. It goes like that. Now, if you put in your theta is 30 degrees, you can solve that. And I just programmed it in my little programmable, which you could do also. And when I put in 30 degrees, let me do that. Let's see, 30 degrees. And this thing will tell me what the velocity is of the piston. It turns out to be 1.6, whole bunch of numbers. We'll just round it off. So there you have it, the absolute method. And if you don't believe me, put in 30 degrees and solve this. You should get that answer. I'm going to do it just to double check here, make sure it works. Here goes. I'm plugging in 30 degrees now. And I hope you are too. Well, I did that, and I got exactly the same answer that I had before. By Jove, that's the absolute method. And if you don't know how I came up with this equation, go back and look at the video for whenever that was. Oh, gee, what is today? This is the 26th. So that would be the 19th, I think. What's 7 from 26? Is it 19? No. It'd be the 21st. Look up the watch the video for the 21st of October. That was last Wednesday, and it'll tell you how to do that. Now to do the instantaneous center of zero velocity method, what you have to do is find the instantaneous center. And do you remember how to do that? I gotta get some feedback here. Hey, Ashley, unmute and say hi, Ashley, please.
Hello.
Yeah, hello, good. I needed to hear a human voice there. Now, here's how you do this. You make your velocity see, that's the velocity of B. And we know what this angular velocity is here of AB. They gave it to us. It's 10 radians per second clockwise, which actually is a negative 10 because it's getting smaller. See, as AB rotates, theta gets smaller. So it's negative. And then the velocity of C is just going straight up. There's the velocity of C. Now to find the ICZV, what you do is you draw perpendiculars to those velocities. Well, see, perpendicular to that velocity puts you up here someplace. Here it is. Not too thrilled with this pencil here. Yeah, that's pretty good. And then you draw a perpendicular to this velocity here. Well, that'll put you right about, there you go. That right there is the ICZV, the instantaneous center of zero velocity. Now we need to find these distances here. I need this little angle here. I could go through that with you if you wanted me to. And let's see here. Maybe I've got it here. We might have to do it from scratch. I don't know. I can't find it. So we can sure do it. I don't like this pencil very good. I like the old days where we wrote on a blackboard. Never mind. All right. To get that little angle there, you go the sine of that angle, call it alpha. How's that? Sine alpha is to, you know what this is? It's 2.5 feet, isn't it? It is to 2.5 feet as the sine of 30 is to they said this is 0.7. Is it 0.75 feet or is it 0.25 feet? I'm getting mixed up here. Let me look. Let's see. No, this is 0.25 feet. That's wrong. You guys, somebody tell me when I do something wrong. It's 0.25. This is 0.75 feet. So this is 0.25 feet. This is 0.75 feet. And you can get the angle up there in the corner. Okay, well, here goes. I'm going to find it. And let's see. 0.5, yeah. Divide by 3, basically. Hit the arc sine button. I'm getting this angle is 9.594 degrees. Okay, so what? Well, see, that makes this angle here. Add those up. Add that to 30. 9.594. Add that to 30. And then when you subtract from 180, here's what you get. You get 140.405. See, those add up to 180. So this angle here is 104.4 is good enough. So you can use the law of sine some more. Sine of 104 is to AB. We need AB. This is A. This is no. We need AC. There we go. Okay, I'm going to find AC now. Here goes. You take the sine.
Isn't it 140.4?
It's absolutely. Honkin', thank you. Was that Ashley?
Yes.
Thank you, Ashley, so very much. It's 140.4. It's not 104.4. It's 140. I'm glad you're awake. Now we're going to find this AC thing here. Okay, well, here goes. You take the sine, multiply by 0.25. Better yet, I'll multiply by 0.75. And then divide by the sine of 30. I'm getting this distance from AC, if you can read my writing, is 0.9560 feet. Ta-da! Now you can get this distance here. You know what that distance there will be? It'll be 0.9560 times the tangent of 30. You guys all took trigonometry in school. So I'm going to multiply that by the tangent of 30. And I get this distance is 0.5519, bunch of numbers. That's good enough. Now we can get this distance here. What I really want is this distance here. What I'm going to do is I'm going to do Pythagoras. I'm going to square that, square this, and take the square root. Here goes. .954 squared. And I'll take the square root. But see, what that gives me is the total distance from, you might call it I to A. I'm getting AI when I do that. And that's a 9.6099 something. What I really want is this distance. So I'm going to subtract 0.25. And this distance is 9.3599 maybe. 9.35. Yeah, that's pretty good. Now I'm ready to get my velocity of my piston. We already did the velocity of the piston with the absolute method, but now I'm doing it with the instantaneous center of zero velocity method. Okay, I got some room here. Let's do this over here. All right. Well, you see, we know the velocity of B. The velocity of B is equal to 0.25 feet times omega of AB. And that's 10. Now it's a minus 10, but we don't care about the minus. We just want that velocity. And I tell you what it is. It's going to be 2.5 feet per second. And it's going like that, right? Maybe more like that. You can see it there. That's the velocity of B. It actually has an angle of 30 degrees. Can you see that? It's got an angle of 30 degrees from the horizontal. That's the velocity of B. Well, we can get the angular velocity. See what I'm saying is the velocity of B is equal to this 9.3599 times the angular velocity of BC. See, every point on this connecting rod is rotating, but it's rotating counterclockwise. See, this connecting rod is rotating counterclockwise as the piston slides up. Okay, we're going to get the angular velocity of our connecting rod. Here goes. We have an equation here where we know the velocity of B, and it's an equation with one unknown. So the angular velocity of BC is, I'm getting 0.267, well, you round it off, I guess, radians per second. Okay, so what? Well, now we can get the velocity of C. There's just enough room here for us. The velocity of C is going to be 0.55196 times the angular velocity of BC. We know what it is. We just got it. Now I'm going to multiply. I'm going to multiply that times the 0.5 times the 0.55196. Well, I didn't get the right answer. I did something wrong. Now, just a minute here. I did something wrong. Let me go back and see what I did wrong here.
How'd you get the 9.3599?
Thank you for asking. We know this is 2.5, right? The velocity of B is 2.5. And we're going to divide by this 9.355. Okay, let me do that. 2.5 divided by 9.3599. No, I think I did that right.
No, I mean like when you got the 9.3599
Yeah.
on your triangle,
Uh-huh.
I didn't get that number.
Oh, thanks for asking. I bet I made a mistake. Let me do that again. Now what I did was I squared this and squared that. Those look pretty good. Those look pretty decent. Let me try that again. 0.9560 squared plus 0.55196 squared. Take the square root. Now what that gives me is this total distance. And here's where I need to subtract this 0.25, right? Okay, subtract 0.25. This is wrong. I'm getting 0.8539 feet from here to here. Anybody getting that? I need an uh-huh. Anybody getting 0.8539?
Yeah.
Yeah, excellent. Now we're going to get the correct value for the angular velocity of our connecting rod. It's not this, I did something wrong there, but we're going to get it now. Here goes. We know the velocity of B, it's 2.5. So I'm getting 2.9277 angular velocity of BC. I bet that's right. Okay, now we're going to get the velocity of C, the piston. We're going to take, no, I think that distance is right, the 0.55196 feet, and now we'll multiply by that. Here we go. Times 0.55196. And I'm coming up with the velocity of the piston is 1.616 feet per second. It's the same numbers there. It goes on for about 10 digits. Exactly the same as what we got using this absolute value, absolute motion equation. And so we have just done this problem two different ways. We did it with the absolute motion method. We did it with the ICZV method. And thanks to, I think it was Ashley that helped me. Thanks to my wonderful students, we've done it two different ways. We've got the same answer both ways. And now I want to show you the relative motion method. I want to show you the relative motion method. I need some room to do it though. And yeah, there might be enough room down here. Let's try it. I don't think we need any of that stuff. I don't know if that's right. I might have done that wrong. Let me erase it. I'm not sure what that was. But I think everything else we have on the board is okay. Now we're going to do the relative motion method. And here's how you do that. You've seen this equation before. I gave it to you a while back. What this reads is the velocity of C relative to B. It's like you had your observer at B and you're looking at C, and what do you see? Well, if you live at B, see, we live on a moving Earth. The Earth is spinning and rotating around the sun, or is it revolving around the sun? No, I think it's rotating around the sun. But we're in motion, constant motion all the time. And when you look out at the stars or the planets, you're really getting a relative motion, you know it? You're getting the motion of whatever you're looking at, like C here, relative to B. B is where your observer is. Here, you can put a little person there. Here we go. We'll put a little person there. There's a person that lives there at B. And when B looks up here at C, strangely enough, this connecting rod is rotating counterclockwise. And so there's a velocity that appears, C appears to be having a velocity like this. This is the velocity of C relative to B. C relative to B. And I can tell you what that angle is. That small angle there, because of geometry, is 9.594 degrees. It's the same angle as this little angle here. Maybe I didn't draw that too perfectly. I think it's maybe a little bit bigger than that. Just a tad bigger, not much. See, that's the velocity of C relative to B. See, this is the velocity of C here, but this is the velocity of C as observed by an observer at B. And so we know what that direction is. Here, let me draw it for you. It goes like this. It goes like this. And the angle that it makes with the horizontal is 9.594 degrees. Okay. Now the velocity of C, we know what it's doing. It's going straight up. Yeah. See, velocity of C is going straight up. We understand that. Now what about B? You know what? We know everything there is to know about B. B is doing this at an angle of 30 degrees, and B has a velocity of 2.5 feet per second. Isn't that right? 2.5 feet per second? Yeah, look here. No. Yeah, the velocity of B is 2.5 feet per second at 30 degrees. There we go. Now all we have to do is write the components for this vector equation. This is a vector equation. This vector right here is the velocity of C relative to B. Velocity of C relative to B. We don't know what that is. And this right here is the velocity of C. And we don't know what that is. But this here is the velocity of B. And we know everything there is to know about it. It's at 30 degrees. It has a magnitude of 2.5. So we have an equation here with two unknowns. We don't know the velocity of C, and we don't know the velocity of C relative to B. So we have one equation with two unknowns. You might think, well, we're stuck. One equation, two unknowns. But it's a vector equation. This is a vector equation. See that equal sign? Those are vectors. And you know, a vector has magnitude and direction, right? So what we can do is we can write two scalar equations. That's what we're going to do. We're going to write two scalar equations. Did you know for every vector equation, you can write two scalar equations? If you're in 3 dimensions, you can write 3 scalar equations. If I had room to write it, I would write that. I would write for every vector equation, there are 2 scalar equations, or 3 scalar equations in 3 dimensions. We're just doing 2 dimensions. Do I need to explain that? Well, I guess not. I need some feedback. Let me see if I can find another wonderful student to say hello. Hey, Braxton, unmute and say hi.
Hello.
Hey, good. I need to know somebody's out there. Okay, well, here's what we're going to do. Why don't we do components? Why don't we do the traditional directions? We'll do the component in this direction. That's what we usually call the x direction. But see, that's going to the left. So the component of that would be a negative 9 point, no. It'd be a negative velocity of C relative to B times the cosine of 9.594 degrees. And then there's an equal sign. See that equal sign? We're writing the scalar equation. Now here, this doesn't have any component in the x direction, so it's just 0. And then there's a minus. See that minus sign? That's in the equation. Now we're going to write the component of this in the x direction, which is 2.5 cosine of 30 degrees. Do y'all, little Southern talk, y'all understand what I did? I just wrote the components in the x direction of this vector equation. Okay, if you understand, now we're going to find what this velocity of c relative to b is. You all have calculators. There's only one unknown in this equation. Get your calculators out and solve for the velocity of c relative to b. Go ahead, I'll wait. I keep banging my computer here. That's not good. Okay, well, let me pick on one of my very best students here. Let's see here. How about Jackson? Jackson, unmute and say hello, please. Yeah. Hey, Jackson, did you get this velocity of c relative to b for me?
Yeah, I think it's a negative 2.196.
Yeah, now we don't want the negative, Jackson.
Yeah.
We just want the amount. I guess you could say it's going to the left, so that's why you said negative. But we know the direction. See, it's going to the left. We even know the angle it's at. But you got it right. It's 2.19. You can round it off to 6 feet per second. Good going, Jackson. Okay. Now what we're going to do is we're going to write the scalar equation in the y direction. I think I got room here. See, the y direction's going up. You know how that works. X to the right, y going up. All right, I'm going to write it. Here goes. Now this has an up component, but see, we already know what this is. It's 2.196. So it's 2. We don't want that minus, so that'd mess us up. It's 2.196. That's how big it is. And you go sine of the 9.594 degrees, because it's going up. And then you put an equal sign. What I'm doing is I'm writing the components of these vectors. This is a vector equation. And for every vector equation, you can write 2 scalar equations. Well, here it comes. That's the component going up. And this is just VC. It's entirely up. Now there's a minus sign in this equation. Now this has an up component. It's 2.5 sine of 30. All I did was I wrote the components of this vector equation in the positive y direction. And looky here, we can get the velocity of the piston. Okay, guys, I'll shut up again. I want you to find the velocity of that piston, and we'll see how we did. Go for it. Okay, I did that. Now let me go to one of my excellent students here. Uh, Jesus, Jesus, unmute and say hola, por favor.
Hello.
Yeah, hello. Hey, Jesus, did you solve for the velocity of the piston using this equation?
Yes.
What'd you get?
1.616.
Well, Shazam. You know what? That's the same answer that we got using the absolute method. It's the same answer we got using the ICZV method. And now we've shown you how to do the relative motion method. Does anyone out there have any questions about the three methods to solve solid body kinematics? Well, okay, if you're happy out there, I'm happy. Let's go on to the exciting world of chapter 17. Unless there's any questions, we're gonna go on to chapter 17. Now, I think I've introduced this, but I forget what I've done. I need to watch my video. But I'm going to erase this whole thing here in about 5 seconds, unless somebody speaks up and asks me something. I'm going to erase it. The whole thing is going to be gone. I've shown you the 3 ways of doing it. Well, okay, nobody said anything. Let me ask somebody out there. How about my friend Stuart? Hey, Stuart, unmute and say hi.
Hello.
Stuart, of these 3 methods, the absolute, the ICZV, and the relative motion method, which one do you prefer? If any, I mean, you might not like any of them, but I mean, if you had to make a preference, which one would you prefer? Earth calling Stuart. Come in, Stuart. What do you think?
So far, I've only really worked with the ICZV, so I guess that one.
Okay, that's fine. Let me adjust this a little bit there. That's better, I think. Yeah. Well, good for you. Okay, well, say goodbye to that. We're going to move on to the exciting world of, well, actually, it's Newton's second law. Chapter 17 is, hey, we've studied Newton's second law before. But see, we did Newton's second law for we did it for particles. We did it for particles. And what particles are bodies that they don't spin. So you can treat them like just a little small piece of mass or a little tiny rock or something. But see, now we're, and what was the equations? Well, we had this one here. But we had them in y too. Remember, we solved them in the 2 directions. Yeah. Oh, but look here. Didn't we also do these also? Does this ring any bells? There we go. That should ring some bells. We studied all that stuff, and then we had it in this business here. We studied Newton's second law for particles, and look at all those wonderful equations that we have there. And you know the names of all that stuff. I could ask any one of you the names of anything we got on here. Like, let me just ask somebody here. Now let me go to somebody. I'll ask them. Ryan, unmute and say hello, please, Ryan.
Hello.
Yeah. Hey, Ryan. Give me the name of this thing here. What's the name of that, Ryan? That thing there. What's the name of it?
Normal acceleration.
Yeah, that's it. Good going. Well, I could ask any one of you guys, any one of these things. Here, let me do somebody else here. Let me find somebody else here. Mark, unmute and say hello, please, Mark.
Hello.
Yeah, hey, Mark. Mark, give me the name of that thing right there, Mark. It's got a name. What's the name of it?
Radial acceleration.
Yeah, that's right. Good. Yes, yeah, I knew it. You guys, you know all that. That's the Newton's second law for particles. But now we're entering a new and exciting world of chapter 17, and it's Newton's second law. If nobody knows what I'm writing there, what I'm trying to write, Newton, I'm too lazy to write it out. It's Newton's second law for solid bodies. And the difference is solid bodies can spin. They can rotate. They're kind of like, weren't we just studying a connecting rod that was rotating counterclockwise? I don't remember the amount, but it was rotating. Yeah, it was rotating. It was a solid body. And Newton's second law is a little different. Not much different. It goes like this. It's the same kind of thing. It's just that the acceleration now is the acceleration of the center of mass of the body. That there's probably better expressed as the center of gravity. But the center of gravity and the center of mass, for our purposes, is the same. There is a slight difference, but for our application, it's the same thing. It's just that when you have a solid body, you've got another equation to worry about. And this equation is called Newton's second law. It's just another form of Newton's second law, where you take the sum of the moments acting on your body about its center of gravity or center of mass, but it's not equal to ma anymore. You see, that's the mass, and this is the linear acceleration or translational acceleration. See, this is not mass, it's called the mass moment of inertia. And this is not linear or translational acceleration, it's angular acceleration. And this thing here is called the moment of inertia, or the mass moment of inertia. Now, in another class that I have, Strength of Materials, we have an area moment of inertia, but we don't do area moments of inertia in this class. We do mass moments of inertia. The units on this thing are kilogram meter squared. Of course, you know what angular velocity is. It's radians per second squared. And if you multiply all that out, you will get Newton meters. Because a kilogram meter per second squared is a Newton, and then you have another meter there, so you got a Newton meter. Well, there you have it. There's Newton's second law for the solid bodies. But right now, today, we're going to spend our time remaining on finding this moment of inertia, this mass moment of inertia. And it's equal to, I could show you where this came from. Maybe I will here in a little while, but right now let's just do this, and I'll try to show you where it comes from here later. But this is the definition of it. It's really a definition. The moment of inertia, or the mass moment of inertia, is the integration of r squared dm. It's got another name. It's called the second moment of mass. And we have a whole table of moments of inertia in the back flap of your book. See, in the back flap of your book, you see this page back here. There's a whole bunch of them back there. One of the important ones is a rod. If you just have a rod, the moment of inertia for a rod is 1/12 about the center now. This is about the center of gravity. Is 1/12 the mass of the rod times the length of the rod squared. I think it'd be fun to derive that. Let's derive that, shall we? Now here's a rod. Here's a rod, and it's of length L, okay? That's how long it is. It's of length L. And see, right here in the center, we'll have a uniform rod is your center of gravity. And what we'll do is we'll say that this rod has a linear density of lambda. Lambda is equal to the mass of the total mass of the rod divided by the length of the rod. That's called the linear density of the rod, mass per length. And what we're going to do is, this will be our x-axis. Take a little tiny differential mass dm at a distance x from the center. We'll shade it in there. You know what that dm is equal to? It's equal to lambda dx. And so when you integrate this, what you'll get is the integration of x squared lambda dx, because the dm is equal to lambda dx. Now we're going to integrate this, and we're going to integrate it from minus L over 2 to plus L over 2. See, L over 2 would be half of the rod going this way, and minus L over 2 would be over here. Okay, we're going to integrate that. Now you guys all took calculus. The lambda is just a constant. You can pull it out, and you'll get the integration of x cubed over 3. And then you have to put in your limits of minus L over 2 plus L over 2. I hope I didn't lose anybody. And then when you put in your limits, here's what you'll have. You'll have the moment of inertia is lambda times L over 2 cubed, which is L cubed over 8. When you cube 2, you get 8. Over 3, now don't forget the 3, minus lambda. Now wait a minute, when you cube that, you get a minus lambda L cubed over 8 over 3. Okay, let's see what we get when we do all this. 2 minuses make a plus, and so what I get is a plus lambda L cubed over 24. See, the 8 goes down in the denominator. 8 times 3 is 24, yeah. And 2 minuses make a plus, that's it. Now keep in mind that L lambda is equal to the total mass, so you could just say M L squared over, well, it's supposed to come out to be 1/12. What did I do? I did something wrong. Now, just a minute. I did something wrong. I did some, yeah, here's what I did wrong. I think you got 2 of these. Because 8 times 3 is 24, but see, you got 2 of these. And so what you wind up with is 1/12 ml squared, and ta-da, we're done. We have just shown you the derivation of the moment of inertia of a rod about its center. But sometimes you need the moment of inertia about a different place, like maybe about the end here. You might want to spin this thing about the end. To do that, you have to use the parallel axis theorem. But before I explain that, are there any questions? Okay, I guess we're all right. We're gonna use the parallel axis theorem. Let me write that up here someplace. This is called, I think it's in the appendix. You could look it up in the appendix. It's called the parallel axis theorem. And the way it goes is like this. See, this is your center of gravity axis, but this is a different axis. I don't know, call it axis A or something like that. Well, it turns out that the moment of inertia about axis A is equal to the moment of inertia about axis G plus the mass times the distance between A and G. Squared. I don't want to lead you astray. Let me see if I can look up that parallel axis theorem in the back of the book here. So I don't want to lie to you. Let's see. Maybe you can find it. Parallel axis theorem. Let me look it up in the index here. Maybe I can find it. Maybe you can find it. Parallel axis theorem. Here we go. Parallel axis theorem. Where the heck is it? I don't see it. Yeah, there it is. Page 414, page 414. Well, that's in our chapter, right? Page 414. Yeah, there's a whole, yeah, there it is. I found it. Ta-da! It's on page 4. This is on page 415 in your book. Can you find it? Now, they wrote there's a little different than I did, but it's the same thing. Boy, Jove, it's the same thing. It's on page 415. Good. Okay, well, if you wanted to find the moment of inertia of this rod about the end here, we can do that. I just need the room here. Here we go. The moment of inertia about the end is going to be your old pal, 1/12 ml squared plus the mass times the distance here. You know what that distance is? It's L over 2, isn't it? Okay, so what's 1/12 plus 1/2? Gee, I don't know. 1/12 plus 1/2. 1/12 plus 1/2. Wait a minute. I forgot something. Somebody could have gotten a thank you point. That's got to be squared. See that square there? So it's not a 12th plus 1/2. It's a 12th plus 1/4, isn't it? Well, what's a 12th plus 1/4? We need to go back to about 5th grade to do that. Let's see, 1/12 plus 1/4. Now, this is what my teacher taught me many years ago. You have to make common denominators, right? Does that make that 3/12? I think it does. Yeah. So you get 4/12. Boy, Jove. Well, what's that? You know what that is? That's a third, isn't it? So the moment about that end there turns out to be 1/3 ml squared. Now, if you look in the flap of your book here, they got it down here, and it says 1/3 ml squared. It's right there where my thumb is wiggling. That's the moment of inertia for a rod about the end of the rod. Any questions so far? Well, here, I promised you I'd show you where in Sam Hill this equation came from. Let me show you that. We got time. Then we'll work some problems. I just need the room here. In case you just tuned in, we're talking chapter 17 today. It's probably the most important chapter in the whole book because it's all about Newton's second law, which is the most important equation in our course, for sure. But I was going to show you where did this thing come from? This thing here. It's got a name. It's called the mass moment of inertia. And here's where it came from. If you take a body, I'll just take a chunk of metal or something. It's somewhere it's got a, I don't know where, maybe here. Somewhere it's got a center of gravity. We all know that. And suppose this thing is spinning. It's got some omega. It's spinning, okay? Well, if you took a little chunk of matter here, this could be a potato, okay? And it's got a center of gravity of the potato. And this little chunk of the potato, call it dm, is at a radius r from the center of mass of the potato. And the velocity of that, if it's rotating about this axis, the velocity of that little chunk of the potato is equal to r times this distance. I don't know what to call it. I don't know. Well, no, we're going to call the distance r, and the velocity would be r times omega. There you go. See, it's rotating with an angular velocity. And so the velocity of that little chunk is r times omega. All right. So what? Well, let's look at the kinetic energy. The kinetic energy of this potato would be the sum of all the 1/2 mv squared. See this little piece of mass here is a dm. So you could integrate this and take the sum of all the 1/2 dm r omega squareds. Does that look right? Yeah, kinetic energy is 1/2 mv squared. And each little piece of mass is dm, and it's got a velocity of r omega, yeah. But you'd have to square it to get the kinetic energy. Yeah. Okay, great. Tell you what, let's pull out all the constants. You know, I think the 1/2 is a constant. And the omega, you know what? That omega squared is a constant. Every piece of this potato is rotating with the same omega. This piece down here is not going faster an angular velocity than any other piece. They all have they're spinning with the same omega. Okay, so you can pull that out. But what you have left is an r squared dm, don't you? Yeah, you have. See, I pulled a half out, and I pulled out the omega squared because it's constant. And what you got left is r squared dm. They just decided to call that, they gave it a name. They called it I, the mass moment of inertia. That's where this comes from. So the kinetic energy of our potato then is 1/2 I omega squared. See, the kinetic energy of translation, where you're just moving in a straight line, is 1/2 mv squared. But the kinetic energy of rotation is 1/2 I omega squared, where this I is your moment of inertia about your center of gravity. Maybe that helps a little bit, help you understand, well, where did this thing come from? Well, that's where it came from. Okay, well, that's good. Let's, do you have any questions? Well, let me tell you this, and then we'll work a problem. There's another way of, instead of giving you a table like in the flap of your book of moments of inertia, and if we only had time, I'd like to do all of these. I would like to derive this round disk and this rectangular plate and so forth. This all these, this ring, that would be fun, yeah. But we don't have time. But I do need to show you about the radius of gyration. There's another way to report the moment of inertia, and it's called the radius of gyration. I think that's how you spell it. It's on page 415. There it is. Yeah, I spelled it right. Page 415. And it's defined, it's really in this equation here. Yeah, there you go. I think they go mk squared, but it doesn't matter. Hope you can read my writing there. This K, that K thing there is called the radius of gyration. And instead of reporting the moment of inertia, they sometimes report the radius of gyration. Kind of weird, probably doesn't make any sense. Why don't we do the rod? See, now the rod, if you have a rod, you know that the moment of inertia of the rod about its center is 1/12 ml squared. Well, that's going to equal to the m times the radius of gyration squared. This really defines radius of gyration. Well, hey, look, we can do a little algebra here. We could get rid of those m's, see there? And the k would equal, what's the square root of 1/12? Just a minute, I can do that. And the square root of 1/12, I did that in my calculator. And let me do this step by step. K squared would equal the square root of 1/12 times L, wouldn't it? Isn't that right? Yeah, I think it would be. And so this turns out to be 0.08333 L. Wait a minute. No, that's just K. I'm getting mixed up. K is equal to the square root of 1/12 times L, which is equal to 0.08333 L. Right? Okay. Well, where is that? Well, it's close to a tenth, isn't it? 0.08. It's close to a tenth. It's a very small distance, really. It puts you about here, maybe. So you see this distance here is 0.08333 L. What they're saying is, if you had a body, a very small body, but it had the same mass as that rod, and it was at a distance of 0.0833 L from your axis here, here's where your G is, you'd get the same moment of inertia for that point body at that distance as you would for this rod. That probably didn't make a lick of sense. I think I can explain it better when we do a problem. Here, let's do a problem, and then we'll run out of time is the sad thing. Well, we have 6 minutes left. Do you have any questions before we work a problem?
I'm getting the square root of 1/12 is 0.28868.
Oh, thank you so very much. I didn't like that. Something was bad about that. 1/12. Yeah, there you go. That I knew that was wrong. I had a really bad. Now, who was that just said? Was that Stuart?
Yes.
Stuart Honkin, thank you. Point for Stuart. Now, 0.28 L. That's between a quarter and a third, isn't it? So that would put you, I don't know, man, a quarter would be about that much, and a third would be even more. Put your, more like that, maybe. Put your mass there. And what we're saying is, if you had your mass at 0.288 L, whatever L is, you could have a meter. That would be cool. Hey, let's do it with a meter. Here we go. We're going to do this with a meter. Thanks to Stuart. You're very helpful. We have a meter stick. It's 1 meter. I got one over here in the corner. Let me get it just a second. Now I've measured the mass of these meter sticks, and they're around, if I remember right, they're around 200 grams. But I don't know, that's my memory, taking a big chance there. Let me get my meter stick. See, here's where I wish we could just have our class face to face. But I have a meter stick here. Ta-da, and you're looking at it. It's so long, it won't fit in the picture there, will it? See it? Look, it's pretty long. And here's the center mass. I don't know if you can tell where the 50, there's the 50-yard line, okay? Well, it's a 50-centimeter line. Now, if you take that meter stick and swing it, I'm swinging it about the 50-centimeter line. There we go. I'm having fun here. Now, if I had a point mass that was at, oh gee, I forgot what it was. Stuart, was it 0.28 centimeters? Is that what it was?
Yes.
Yeah, 0.288 meters. I'll tell you where that is. That's, see, here's the 50 right here. I've got my finger on the 50. 28 would be, there's 10, there's 20, there's 28. There, where my finger is. If you had a mass of 200 grams, and you had it at 0.288, well, that puts you more than a quarter of the way. See, 0.288 puts you here. See, 75 is right here. This is 50, 75, 100 centimeters. 28 centimeters puts you right here. If you had a mass of 200 grams, and you put that mass, take a string and tie that mass, have the string 28.8 centimeters, and just swing that 200 grams around and around. It would have the same feel. It would have the same feel and difficulty of rotation as the meter stick. I don't know, maybe that helps you a little bit. We'll see. Okay, well, we got time. Oh, no, we don't have time. See, when you have you noticed when you're having fun how fast the time goes? Well, you got homework. I could write it down, but it's in your Blackboard there. And this time there hopefully won't be any confusion. Maybe you'll understand it because it's pretty clear. If I had time, I'd work some problems, but we'll get together on Wednesday, and we'll do some problems on Wednesday. Here's your last chance to say anything. Do you have any comments or questions for me?
Thank you for everything you do, sir. You're a wonderful professor.
Whoever that was, they just got an A. Now let me mark that down before I forget. I'm just teasing with you guys. Thank you so much, each one of you, especially those of you that know how to take the square root of 1/12. That's good. Well, bye-bye till Wednesday. Bye-bye, students.
But
Bye.
Bye.